It is a statement, or it is a variable, or it is an argument. It has the two possible values, either of the two possible values, 0 and 1. This NOT operator takes only one input and only one output. One output is nothing but it is called as complementation. In SOP form, we are considering the Minterm equations. In PUC form, we are considering the Maxterm expression. So these are two forms of canonical expression. Dear students, welcome to Computer Science Revision classes. I am Ravi Kumar Kyar, lecturer in Computer Science, Vidhyaashram PU College, Temple of Excellence, Mysuru. Students, let us start our revision classes with the chapter Boolean Algebra, chapter number 2. The weightage of the chapter is 10 marks. Here, one MCQ or one MCQ, and there are two 2 marks question for 4 and one 5 marks question. So total weightage of the chapter is 10 marks. Now, in Boolean Algebra and in the revision classes, we are going to cover the important concept of the chapter Boolean Algebra. And here, let us start with introduction to Boolean Algebra. First, let us see what is an algebra and Boolean algebra. An algebra that deals with the binary numbers are called Boolean algebra. Now you know what is a Boolean algebra. Here it is nothing but it deals with a binary numbers. If I talk about binary numbers, you know there are two values, that is 0 and 1. They are called binary numbers, and the concept, the algebra that deals with binary numbers are called Boolean algebra. In general, Boolean is the value, it is a data type, so it contains or takes the two possible values, either 0 or 1, or it is a state, it takes the values 0 and 1. That is the reason it is called as Boolean algebra. And here it is known as Boolean algebra, and it is useful in designing logical circuit, and it is used by processor. Now we know what is a computer microprocessor. So microprocessor is the main component of a computer system, and it is made up of number of logical circuits. And in logical circuit in turn is built with the help of the Boolean algebra. Now the elementary logic gates that are used to build up circuits of different types of perform necessarily arithmetic operations. So it is possible to have different logical gates, and with the help of this we can have a different logical circuit for different arithmetic operations. And it is used to design simple logic circuit, frequently used by ALU of arithmetic logic unit and of all computers. Now we know that the CPU of a computer is made up of, or it contains, there are three parts, that ALU, control unit and memory unit. So here this Boolean algebra is used to design simple logic circuits, and these are the logic circuits frequently used by ALU of CPU for different arithmetic and logical operations. So this is the definition of Boolean algebra. In the next slide, we will see what are variables in Boolean algebra. So what are variables? So a variable used in a Boolean algebra or Boolean equation can have only two possible values. So it is a variable to store any of the two possible values. So the two values are false or true, or we represent 0 and 1. Here 1 stands for true and 0 stands for false. So the truth values are these are called truth values. The truth values are depicted by logical constant true and false, or 1 and 0 respectively. So here this 1 and 0 are called logical constants, and so logical variables which holds either of the values, either 0 and 1. So 0 and 1 are called logical constants. Next one is truth table. So what is a truth table? It is a table which represents all the possible values of logical variables or statements along with the possible results it is a combination of values. So what is a truth table? Now we know what is the truth values. 0 and 1 are called truth values, and we know what are variables. I mean, is a variable in a Boolean algebra, it is a statement, or it is a variable, or it is an argument. It has the two possible values, either of the two possible values, 0 and 1. So here truth values. So what is a truth table? So truth table which represent all the possible values of the variable, a logical variable, along with the possible output of the particular combination. So we are storing it in the form of a table, that is called as a truth table. And another definition is, it is a table of truth values of truth function. So this is the definition of truth table. In the next slide, we will see logical operators. So what are logical operators? Here, these are the operators, not, or, and operators. These are the operators to perform logical operations in Boolean algebra. Now let us see what is logical operators. So here, first one more definition called Venn diagram. So what is Venn diagram? A Venn diagram is a diagram representing the logical sets, particularly as a circle or closed curve with an enclosing rectangle. So look at the example here. Look at this example diagram here. So what is a Venn diagram? So we are representing the logical sets of the result or the variables with a rectangle and or a circle or a semicircle or an arc. That is nothing but a Venn diagram. So now let us see what is a not operator. So one of the logical operator is not operator. So what is not operator? So definition is, this operator operates on single variable. It operates on single variable, means it takes only one input. And operation performed by not operation is called complementation. And the symbol we used is bar. Suppose if you observe this here variable x is, suppose if you take variable is x, this is a one variable, logical variable which hold the values either 0 or 1. And what is x naught, or you say x bar, you say x and this is bar. So this is how we represent not operator, and this is not operation. And this operation we are representing through Venn diagram like this. And this is a truth table. So now if you observe that this not operator takes only one input and only one output. One output is nothing but it is called as complementation. It means that, so it takes one variable. So one variable can have two possible values or two possible status. So one is 0 or 1. And what is the output of this? If the variable is 0, input is 0, output is 1. If the input is 1 and output is 0, so this is how we represent the truth table for not operator or not operation. So here only one variable, there are two possible combinations. So this is a truth table and Venn diagram for not operator. In the next slide, let us see what are OR operators. So, an OR operator which denotes operation called logical addition, and the symbol used is plus. So, OR operator which represent logical addition, we use the symbol plus. Now observe this here. See, this is called OR operation. This one is plus is the OR operator. So it takes two or more input signals or two or more input. So in this there are two variables, one is 0 and one is here, one more 0 here. If there are two variables, so we can have four different combinations. So here 0 plus 0 equal to 0 and 0 plus 1 is 1, 1 plus 0 is equal to 1, 1 plus 1 is 1. So this is a OR operation. It works on two variables. In this example, this is one variable and this is another variable. This is the result of OR operation. Now, look at the truth table for this. Here there are two variables x and y. This x and y are two different variables, or two variables for OR operation. If there are two variables, we can have four different combinations. So here this is 0, 0 is one combination, 0, 1 and 1, 0 and 1, 1. So this is nothing but the truth table, and here the result is here x plus y plus denotes the OR operation. So what is this is nothing but binary addition. If you look at the binary addition, look at the table here. What is 0 plus 0? 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0, 1. 1 plus 1 is 1. So this is the binary addition or logical addition. This is OR operator and OR operation. Now this is the Venn diagram. We represent OR operation with this Venn diagram. In the next slide, AND operator. Another logical operator is AND operator. So AND operator, it performs logical multiplication, and we used to represent with the symbol dot. So this is dot. So plus stands for logical OR operation, and here dot stands for logical multiplication, that is AND operation. Now accordingly, this is the operation. So here 0 and 0. This is here dot stands for AND operator. So 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. So this is the logical multiplication. And if we look at the truth table for this, there are two variables x and y, and as we have seen in the previous slide, it can have four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Now, by looking at this operation, we can write the output here, and here x and y. This AND, it represents AND operation or AND operator. So 0 plus 0, 0 into 0, or 0 and 0, 0, 0 and 1, 0, 1 and 0, 0, 1 and 1 is 1. So this is the truth table for logical OR operator. This is a Venn diagram. X and y are two different variables. Next concept is, another important concept is in Boolean algebra, that is principle of duality. So what is the definition of this? See, this is an important principle used in Boolean algebra. So this, what is the definition of this? It states that starting with a Boolean relation or equation, another Boolean relation can be derived. I mean, starting with one equation, we can derive at another equation. How? By changing each OR sign to AND sign, and on AND sign to OR sign, and changing 0 by 1 and 1 by 0 in Boolean equation or Boolean circuit. So this is the definition of principle of duality. So for example, the derived relation using duality principle is called dual of original expression. So we'll start with an expression that is the original expression. The final result after the principle of after applying the principle of duality, we are deriving a new circuit or new statement, that is the duality of, that is called as dual of the original expression. Now for example, we take a postulates of OR relation. In the OR relation or OR operation, we know that 0 plus 0 is 0. So from 0 plus 0, we can derive at one more equation. Now how is possible? By changing 0 to 1 and 1 to 0, and by changing plus to AND operator or AND to OR operator. Accordingly, we change 0 to 1, and here plus to AND operator, and this 0 to 1 and equals this 0 to 1. So it is 1 and 1 that equal to 1. So this is a new circuit or a new equation. This is nothing but this logical AND operation. We have started with, in this example, we have started with the OR operation, and we have converted this into AND operation with the help of principle of duality. So similarly, 1 plus 0 equal to 1, and after changing this it becomes 0 and 1 equals to 1. It is logical multiplication. So or a logical AND operation. So this is the concept of principle of duality. Now in the next slide we will see what are all different theorems in Boolean algebra. So in Boolean algebra we will come across different Boolean theorems. It start with properties of 0, properties of 1, and idempotency law, involution law, complementarity law, commutative law, associative law, distributive law, absorption law, and distributive law. All these are, this is another form of distributive law. It is called as third distributive law. And see, these are all different theorems or we are using in Boolean algebra. So the students are to be thorough with all these different theorems to solve any equation or Boolean equation. Now in the next slide we will see next concept is a logic circuit. So how to write a logic circuit or how to build a logic circuit for the given equation. Now I take an example like this. So this is distributive law. This is distributive law. X into y plus z equals to xy plus yz. Now what is the logic circuit for this distributive law? If you observe this, here y plus z is R operator, y plus z is R operator, and is x and here. So this is AND operator here. So it is AND operator. So AND operator and here. So here x, this is one input, x, y plus z is another input for this AND operator. And then equals, this equals x into y, and here we have R operator, this is R operator, and in between we have xy. It stands for x and y. It is nothing but AND gate or R operation, AND operation. So accordingly, this AND gate, x and y, it is xn plus y, xy here, x plus z. So it is R. So this is a distributive law or a logic circuit for distributive law. Now in the next slide we will see any logical, any Boolean equations or Boolean theorems. We can prove this by three different methods. One is by perfect induction method, second one is by truth table method, or next one is by algebraic method. So any given Boolean theorems we can prove it by three different steps or three different methods. I repeat, they are: one is perfect induction method, algebraic method, and by truth table method. Now let us see, we prove distributive law by perfect induction method. So in perfect induction method, we have to prove the theorem by giving a value 0 and 1. So for the variable x, first we have to assume that we have to give the value x equal to 0. We have to prove this, and again we have to give x equal to 1, then we have to prove the theorem. So that is the perfect induction method. So for example, if you look at LHS of this, so if you look at the this one equation, LHS is x into y plus z. So x into y plus z, that is the left hand side. So here first assume that let x equal to 0. So 0 and here y plus z. So here y plus z. See, what is y plus z? Here there is no value for x here. So 0 into y plus z, that equal to 0. This again as per the Boolean theorems, that is properties of 0. And similarly RHS, right hand side, we know the equation of right hand side, that is xy plus xz. So in xy plus xz, you substitute 0 for the variable x. Accordingly, 0 into y plus 0 into z, and 0 into y, this is equal to 0 into 0 and 0. This is based on the Boolean theorem, that is properties of 0 and properties of 1. So we have proved here LHS equals to RHS. Now again we have to prove the same theorem with the value of x equals to 1. Accordingly, you will get LHS equals to RHS. So this is one method of proving Boolean theorem. In the next slide we will see how to prove this by truth table method. Now you know how to draw truth table for this. If you look at this distributive law, and here if you observe this, we have this LHS. On LHS we have x into y plus z, and this is xy and yz. So in this example we can see there are three different variables x, y and z. So first we have to draw a truth table for three variables truth table. So accordingly, so here there are three x, y, z, the three variables, and there are three variables, and we can have 8 different combinations. So 2 to the power of 3, that is equal to 8. We can have 8 different combinations, and now we have to prove with a different combination of given in the theorem. So first one is say y plus z. So y plus z, here this is y and this is z. So we have to, this is plus is logical addition. So 0 plus 0, 0, 0 plus 1 is 1. So accordingly, we have to fill this column. Next again, next combination is x and y. Here x dot y or and y. This is logical multiplication. So x and y, we consider these two. Here 0 into 0, this is 0. This is logical multiplication. 0 into 0, 0. So accordingly, we have to follow this. So in this one, we are working with logical addition or logical multiplication or and or operator. So this is another combination, and x into y plus z, this is another column, and this is xy plus yz, this is another column. So once if you complete this truth table of the given three variable with the three variables, now if you look at these two columns, if you look at these two columns, and these two columns are same. So because of this, the columns x into y plus z equals to x in xy plus yz. So hence the theorem is proved. So this is another method of proving the Boolean theorem. This is truth table method. In the next slide, we will see how do we prove this by algebraic method. So algebraic method is the proving the theorems by following or the Boolean theorems of Boolean algebra. So accordingly, say this is the another method of proving Boolean equations or given Boolean theorems. Now in the next slide, we will see the De Morgan's theorem. This is one of the important theorems in Boolean algebra. So this is, it states that not x plus not y equals to not x into not y. So this is the first De Morgan's theorem, and this is a logical circuit for this. And here, in order to prove this Boolean theorem, we are following complementarity law. That is, first one is, let us assume that p equal to x plus y and p, x, y are the variables. And according to complementarity law, it is p plus p naught equal to 1 and p into p naught equals to 0. So to prove this De Morgan's theorem, we have to follow complementation law or complementarity law, that is p plus p naught equals to 1 or p into p naught equals to 0. So here, let us assume that this is the theorems proved here. It means that here Boolean variables, let p equals to, in the previous slide, we assume that let p equals to x plus y. Let us assume p equal to x plus y. So if p equal to x plus y, then p naught equals to not x plus not y, that is equals not x into not y. So this is 1. So if you want to prove that, we know what is p plus p naught equals 2. So here p equal to this and p naught equal to the value here. So this must be equals to 1. So accordingly, x plus y plus xy must be equals to 1. We have to prove this. And one more equation is p into p naught equals to 0. So this is p into p naught must be equal to 0. We have to prove these two conditions by algebraic method. So then we can prove the De Morgan's theorem. So this is, we have proved De Morgan's first theorem. Now De Morgan's second theorem. In De Morgan's second theorem, it states that not x into not y equal to not x plus not y. This is De Morgan's second theorem, and this is how to draw a larger circuit for this De Morgan theorem. And again we have to prove this theorem also by following complementarity law, that is p plus p naught equal to 1 and p into p naught equals to 0, or x plus x naught equal to 1 and x into x naught equal to 0. So it is another De Morgan's second theorem. This is how we have proved algebraically. Next we'll see what are all different applications of De Morgan's theorem. So here the De Morgan's theorem are useful in implementation of basic gate operations, that is particularly with NAND and NOR gate, which are readily available in IC form. So this is another application of Boolean De Morgan's theorem. And next one is it is used in simplification of Boolean expression. That is what we have proved the algebraic method. Next one is it is commonly applied with text searching using Boolean operation and or not. See, normally when we are looking for some information in the internet, we can also make use of this and or keywords and not keyword. This is nothing but a logical operations, and it is another application of De Morgan's theorem. Now the De Morgan's theorems law are example for more concept of mathematical duality. So these are all different applications of De Morgan's theorem. Next concept is derivation of Boolean expression. Now here there are two concepts, one is Minterm and Maxterm. Now let us see, first one is what is a Minterm, and please remember in the Minterm form value of x equals to 1. This one you have to keep in your mind. So what is Minterm? It is a product of all the literal. What is Minterm? Minterm is product of all the literal with or without the bar within logical system. So this is a Minterm. One more definition is Minterm. It is product of all the literals. So for example, if x equal to 0, y equal to 1 and z equal to 0. See, these are all called literals, Minterm. These are x, y, z are called literals, or another name is variables. So here if x equal to 0, y equal to 1, z equal to 0, then what would be the Minterm expression for this? So it is nothing but product of all the literal, so with or without bar. And as I told you here, Minterm here in the variable value of variable x equals to 1 means non-barred letter or non-barred literal has a value 1. So accordingly, if I say 1, so if it is 0 means it's supposed to be x naught. So we are writing here x naught and dot, this is a product, it stands for product of the literals. So again y equals to 1, so we have to write y as it is, and here z equal to 0. So in this example, in Minterm form, it's supposed to be x naught. So this is how to write a Minterm expression for the given literals. This is product of all the literals. There are three literals, x, y and z. You take another example. If x equal to 1, y equal to 0, z equal to 0, then the Minterm expression will be for x is x, is 0 is y bar and z bar, or it is x, y naught and z naught. So this is how we derive, or how do we write Minterm expression for the given values of literals. In the next slide, another definition is Maxterm. So in the Maxterm, here value of x equal to 0 means in Maxterm the value of non-bar literals is equal to 0. So accordingly, it is sum of all the literals with or without the bar within the logic system. So in the previous slide, we have seen Minterm, it is product of all the literals, whereas in Maxterm, it is sum of all the literals. For example, here if x naught equal to 0, y equal to 1 and z equal to 1. So then how do we write the Maxterm expression? Here we are using plus because it is sum of all the literals. So here in Maxterm form, x equal to 0. Here x not equal to 0 will be x plus, and why not? Here value of non-bound letter will be 0, but here is 1, so it is why not, and that is again z. So this is nothing but, this is how we write Maxterm expression for the given value of literal, and it is sum of all the literals. In the next slide, next definition is, what is a canonical expression? A canonical expression can be represented in the following two forms. One is sum of product form, and second one is product of sums form. It is one we say SOP, and second one is POS. SOP stands for sum of products and POS stands for product of sum. So any Boolean expression composed entirely either Minterm or Maxterm is referred as canonical expression. So what is a canonical expression? So it is nothing but any expression, Boolean expression composed of either a Minterm or Maxterm is referred as canonical expression. Now let us see what is SOP or sum of products form. So when a Boolean expression is represented purely as sum of Minterm, it is said to be canonical SOP form. So here in canonical expression, if represent with sum of Minterm, it is referred as sum of product form. And in product of sum, here when Boolean expression is represented by or purely as product of Maxterm, then it is said to be canonical product of sum form. So please observe here, in SOP form, we are considering the Minterm equations. In POS form, we are considering the Maxterm expression. So these are two forms of canonical expression. Students, so far we have discussed the few important concepts of Boolean algebra. Now let us continue our discussion in my next class. Thank you so much.